Welcome to Senior High School Mathematics. Let us have optimization using calculus. This is part 2 of 2 parts. Application of Extrema to real-world problems under basic calculus. Many real-life situations require us to find a value that best suits our needs. If we are given several options for the value of a variable, how do we choose the best value? Such a problem is classified as an optimization problem. We will now apply our previous discussion to finding extremum values of a function to solve some optimization problems. If you haven't seen the previous video lesson, the link is on the description of this video. Here are some suggested steps in solving optimization problems. Draw a diagram that illustrates the situation in the problem. Next, represent all unknown quantities involved using variables. Identify the objective function. This function must be continuous. Identify the quantity, say Q, to be maximized or minimized. Formulate an equation involving Q and other quantities. Express Q in terms of a single variable, say X. If necessary, use the information given and relationship between quantities to eliminate some variables. The objective function is maximized, Q is equal to f of x, or minimized, Q is equal to f of x. Determine the domain or constraints of Q from the physical restrictions of the problem. Use the appropriate theorems involving extrema to solve the problem. Make sure to give the exact answer to the question. Let us have an example. Find the number in the closed interval -2, 2 so that the difference of the number from its square is maximized. Here is our suggested solution. Let x be the number, where x is an element of the closed interval -2, 2. Hence, we want to maximize the function f of x is equal to x squared minus x. This is the difference of the number x from its square, x squared. Note that f or the function is continuous on the interval -2, 2. From the extreme value theorem, we find first the critical numbers of f in the closed interval -2, 2. The derivative of f of x is equal to x squared minus x is f prime of x equals 2x minus 1. 2x is the derivative of x squared and -1 is the derivative of -x. From here, we get the critical number. We equate f prime of x to 0. So we have 2x minus 1 equals 0. Then, we only have one critical number in the interval -2, 2, and that is x is equal to 1/2. Then we compare the function values at the critical number and the endpoints of the closed interval -2, 2. Solving, we have f of -2 is equal to -2 squared is 4 minus -2, that will be 6. Then let us have f of 1/2, that is our critical number. So we have 1/2 squared is 1/4 minus 1/2, that is -1/4. Then we have f of 2, the other end of the closed interval, that will be 2 squared minus 2, and that is equal to 2. Then from here, we conclude that f attains a maximum value on the closed interval -2, 2 at the left endpoint of the closed interval. Therefore, the number is -2. Let us have another example. A piece of wire 10 feet long is cut into 2 pieces. One piece is bent into the shape of a circle and the other into the shape of a square. How should the wire be cut so that letter A, the combined area of the two figures is as small as possible. Letter B, the combined area of the two figures is as large as possible. Here is our suggested solution. Let x be the length of that piece bent into a circle. That implies that r, or the radius of the circle, is equal to x over 2 pi. Since the sum of the two perimeters is 10 feet long, then 10 minus x is the perimeter of the square, or the length of that other piece bent into a square. And this implies that the side of the square is 10 minus x over 4. Let A of x in square feet be the combined area of the circle and the square. Hence, A of x is equal to the sum of the areas of the circle and the square. For the circle, we have pi r squared. So pi times the quantity x over 2 pi squared, plus, for the square, 10 minus x over 4 squared. Simplifying the right-hand side of this function, we have A of x is equal to x squared over 4 pi plus 100 minus 20x plus x squared over 16. In here, x is an element of the closed interval 0, 10. Let us have the derivative of A of x. That will be A prime of x is equal to x over 2 pi. That is the derivative of x squared over 4 pi. Minus 5/4, that is the derivative of negative 20x over 16. Plus x over 8, that is the derivative of x squared over 16. And the derivative of 100 over 16 is equal to 0. This implies that we can get the critical number at x over 2 pi minus 5/4 plus x over 8 equals 0. And x is equal to 10 pi over 5 plus 4. Now we will get the function values at the ends of the closed interval 0, 10 and the critical number 10 pi over pi plus 4. A of 0 is equal to 25 over 4. That is, when x is equal to 0, x squared over 4 pi is 0, x squared is 0, 20x is 0, so we have 100 over 16, 25 over 4. Next, A of 10 pi over pi plus 4, substituting 10 pi over pi plus 4 to x. In the function, we have A is equal to 25 over pi plus 4. Lastly, we have A of 10, substitute x is equal to 10 to the function A of x. We will get 25 over pi. 25 over pi plus 4 is approximately equal to 3.5, and 25 over pi is approximately equal to 8. Therefore, A has an absolute minimum value when x is equal to 10 pi over pi plus 4, and A has an absolute maximum value when x is equal to 10. To answer the questions in the problem, letter A, the combined area of the two figures is as small as possible. The combined area is smallest when x is equal to 10 pi over pi plus 4. So the radius of the circle is 10 pi over pi plus 4 times 1 over 2 pi, and that is 5 over pi plus 4 feet. And the side of the square will be 10 minus x over 4, that is equal to 1/4 of 10 minus 10 pi over pi plus 4. And this is equal to 10 over pi plus 4 feet. Letter B, the combined area of the two figures is as large as possible. The combined area is largest when x is equal to 10. That is when the radius of the circle is 5 over pi feet and there is no square. Let us have example number 3. A farmer has 2,200 50 feet of fencing material and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Here is our suggested solution. To solve the problem, we first draw a picture that illustrates the situation. Let x be the width of the field and y be the length. The next step is to create a corresponding mathematical model. From the problem, we are to maximize the area. That will be A is equal to x times y, or that is width times length. Our constraint is that the fencing material that the farmer has is 2,200 feet. Then we have y, the length, plus 2x is equal to 2,200. We now solve the second equation for y and substitute the result into the first equation to express a as a function of one variable. So from y plus 2x is equal to 2,200, we have y is equal to 2,200 minus 2x. Substituting this value of y to the function that is to be maximized, then we have a function in x, or the area as a function of x. We have a of x is equal to x times y, that is 2,200 minus 2x. Simplifying, we have a of x is equal to 2,200x minus 2x squared. In here, x is an element of the closed interval 0, 1,100. So we get the derivative of a of x, that is a prime of x is equal to 2,200 minus 4x. And to get the critical number, we have 2,200 minus 4x equals 0. We get 2,200 is equal to 4x. Dividing both sides by 4, the only critical number that we have is 550. Now we get the function values at the endpoints of the closed interval and the critical number. A of 0 is equal to 0. That is substituting x is equal to 0 to a of x. The critical number 550, so we have a of 550, that is 2,200 times 550 minus 2 times 550 squared, and we get 605,000. Lastly, we have a of 1,100 is equal to 0. Therefore, the maximum area of the field is 605,000 square feet, and the dimensions are: the width is 550 feet and the length is 1,100 feet. Let us have one more example. We want to construct a box whose base length is 3 times the base width. The material used to build the top and bottom cost 100 pesos per square feet, and the material used to build the sides cost 60 pesos per square feet. If the box must have a volume of 60 cubic feet, determine the dimensions that will minimize the cost to build the box. Here is our suggested solution. First, let us draw the figure and illustrate the dimensions of the box. Let W be the base width, L be the base length, and then H be the height. Since the base length is 3 times the base width, we have L is equal to 3W. From the given information, we are to minimize the cost, and that will be equal to 100 times the materials used to build the top and bottom, that is length times width. So we have 100 times 2LW, and since the material used to build the sides cost 60 pesos, we have 60 times the quantity, 2 times WH, plus 2 times LH. Simplifying, we have 200 LW plus 60 times 2WH, that is 120 WH. 60 times 2LH, that is 120 LH. And since L is equal to 3W, we will substitute L is equal to 3W and get 600 W squared plus 120 WH. 120 times 3W, that is 360 W times H. Simplifying further, we have C is equal to 600 W squared plus 480 WH. Also, from the given information, our constraint is that the volume must be 60 cubic feet. So from here, length times width times height is equal to 60 cubic feet, and we will get an equation for H in terms of W. So we have H is equal to 60 over 3W squared, that is LW. Substituting L is equal to 3W, we have 3W squared in the denominator. 60 over 3 is 20, so we have H is equal to 20 over W squared. Now we can express C as a function of W by substituting H is equal to 20 over W squared in the equation for C. Hence, we have C of W is equal to 600 W squared plus 480 W times 20 over W squared. Simplifying, we have 600 W squared plus 9600 over W. The domain of this function is from 0 to positive infinity. Hence, we will use the first derivative test for absolute extreme values. Suppose that C is a critical number of a continuous function f defined on an interval. Letter A, if f prime of x is greater than 0 for all x less than c, and f prime of x is less than 0 for all x greater than c, then f of c is the absolute maximum value of f. Letter B, if f prime of x is less than 0 for all x less than c, and f prime of x is greater than 0 for all x greater than c, then f of c is the absolute minimum value of f. This time, let us have the derivative of c of w. So we have c prime of w is equal to 1200 w, that is the derivative of 600 w squared, minus 9600 over w squared, that is 9600 over w. From here, we will get the critical number by equating c prime of w to 0. Then we have 1200 w minus 9600 over w squared is equal to 0. Multiplying all terms of the equation by w squared, we have 1200 w cubed minus 9600 is equal to 0. 1200 w cubed is equal to 9600. Then w cubed is equal to 9600 over 1200, and then we get w is equal to 2. The only critical number is 2, and from here it is clearly to see that c prime of w is less than 0 for all values of w between 0 and 2. Also, c prime of w is greater than 0 for all w greater than 2. Therefore, the minimum value of cost must occur at w is equal to 2. Hence, the dimensions are width is equal to 2 feet, length is equal to 6, that is from 3 times w, 3 times 2 is 6, and h is equal to 5 feet. From h is equal to 20 over w squared from the previous slide. That is 20 over 4, 5 feet. If we are asked what is the minimum cost, we can get that by substituting w is equal to 2 from the equation for c. Then we have c is equal to 600 times 2 squared plus 480 times 2 times 5. And c, or the minimum cost, is 7,200 pesos. In our next video lesson, we will discuss another application of the derivative, and that is solving problems on related rates. That will be all. Thank you for watching. Please subscribe for more math lessons.